you can find it at eco.ucdavis.edu. And just so you understand where my team sits in facilities, we have both a controls and energy engineering side that does energy projects and engineering work on campus in the buildings mostly. And that's on the left side of the screen here. That's with our energy engineering team, which is actually self-funded out of the savings that they get from projects on the campus. We also have students working for them, like grad students. Reese's picture is on there. We like to work with the Energy Graduate Group and get their involvement on these projects. And then we also have a controls engineering team that implements a lot of those projects, as well as upgrades control systems in the buildings and maintains those. So the other side of our team is what I call the fun side. They're the engagement, outreach, education side, and that's part of what we're trying to do on campus, and probably a little different than most facilities groups. But my boss has been really big on trying to make sure we have that connection with the campus. That's what we're here for as a campus, and so obviously doing things like this where we can educate people about what's going on behind the scenes, as well as get students involved. And we have, we sponsor classes and bring projects to classes. And so things like that, I think, are really important being on a university campus. And that makes it really exciting. And also just educating the people in the buildings that we're working on, so that we can better tune those buildings and get the people in the buildings involved in the projects. So feel free to look into our team more on our website. But today I'm going to talk about the heating and cooling systems and our large electrification project that's part of our carbon neutrality goal by 2025. So if you don't know UC Davis, I know most of you do, but we're a big campus, a lot of land, a lot of buildings on that land, and about 8 million of the 12 million square feet that we have on the Davis campus is connected to our heating and cooling systems, district heating and cooling. So that's what I'm going to be talking about today. We spend a lot of money on utilities, which is partly why my team exists. We're trying to not waste any of that money, make sure it's getting spent well, and cut as much as we can. So, but we're usually around 25 million in annual utilities, and a good chunk of that goes to heating and cooling. The typical daily population, not including the last year, is over 35,000 people on campus. About 7,000 of those are residents, the first year students living in the dorms, but the rest are daily visitors. This last year, we've had real low numbers, about 10% of that at peak. So with the pandemic, there's most people are working remote. So there's still a lot of labs going on campus, a lot of research, and then things like our vet med buildings are still fully operational. But other than that, it's been a pretty different scene, and that's a whole nother story, another presentation. But what I want to talk about today, when people talk about electrification, the first thing usually they're thinking is solar PV, especially. And we've got that. This is our 16 megawatt PV system. If you haven't seen it, this is what it looks like from the Levy Road south of campus off of Old Davis Road. You can see the campus water tower off in the left of this picture. Here's a high aerial view of that same farm. It's 62 acres and right on the south edge of campus. And you can see UC Davis there in the background with the city of Davis around it. This is, as far as I know, the largest solar farm on any campus in the US, maybe in the world, because most campuses don't have this much land to turn into solar. But so that's been a real big opportunity for us. It produces about 15% of our annual electricity. And but you can see on a daily scale, this is a chart from our energy dashboard. You can feel free to check out at some point if you haven't seen it. But this shows campus electricity demand in the dark green there, and the solar farm production in the yellow. And what you can see is that there's times where the the solar is producing about half of our campus demand in terms of electricity. So that's pretty exciting just from on-campus power. We also have another 30 megawatts off campus, and that combined with our hydropower, which we get through our electrical purchasing agreement, we are very close to 100%. I wouldn't say renewables, but fossil free. Hydropower is not always considered renewable, but it is carbon free, and so carbon free power is our goal, and we're very close to that, and we'll definitely be there before 2025 on the electric side. What people don't often think about when they think about electrification, or what the bigger challenge, I should say, is getting into the heating side, which is typically done by gas or fossil fuels. So when you look at a campus like this, though, I don't know what strikes you, but the thing that makes me think about is the number of existing buildings that are out there. When we talk about electrification or carbon neutrality, the biggest challenge by far is what to do with the existing footprint. Anybody can build new buildings that are very efficient, possibly zero net energy or carbon neutral. That's being done often now, but the bigger challenge is what do you do with that existing footprint of buildings, which we have quite a few. So what you don't see in this picture, though, is what's underground, and that's where the district energy comes in, and that for us is one of our biggest opportunities. This is the case on a lot of campuses. Not all the UCs have the opportunity that we do with the district energy, but a lot of them are looking at it. And at this point, I think we're the farthest along in terms of actually implementing a campus-wide electrification project. But here's a map that does show you what's going on underground. A couple maps. On the left is our cooling system, and that is, these are each about 27 miles of pipe when you include supply and return systems and all the branch lines to all the buildings. On the cooling side, we're supplying cold water out to the buildings at 40 degrees and comes back at 60 degrees approximately, at least design. And on the heating side, we're supplying steam at 350 degrees, about 130 PSI. And then that steam is doing heating and heat exchangers in the buildings, mostly heating hydronic loops within the buildings. And then it comes back as condensate or hot water at around 200 degrees. And so the challenge for us is right now that steam system is heated by natural gas, and these two district energy systems are completely independent. So if you take the loads from those two systems and you put them on a chart with the heating on the negative y-axis and the cooling on the positive, you can see how they compare to each other. And that's what we started doing years ago and looking at a real opportunity. And the opportunity is that when you look at daily heating and cooling loads, there's actually some opportunity for heat recovery. And that's a really significant opportunity. And one way to think of it is that all that cooling is removing heat from the buildings. And what are we doing with that heat right now? We're just throwing it away in our cooling towers. So our cooling system is collecting heat from the buildings to cool them off, taking it back to our chillers at the central plant. The chillers move that heat into the condenser water system and it rejects it out into the atmosphere at the cooling towers. So all that blue is heat we're collecting from the buildings to cool them off and just throwing it away. And then all the red, we're burning gas to make heating. The missed opportunity is, can we use that heat to do some of our heating? And just looking at these numbers here, yeah, you absolutely could. If you can do daily storage, the heating and cooling is not always at exactly the same time, but if every day we're doing heating because the temperatures drop to, almost every single day of the year, they're down below 65 degrees. Even in the summer here, we're getting down to 65, 70 degrees at the highest in the summer at night. And so the campus buildings, which are running continuously, which are all the lab buildings, are doing heating throughout the night. That, that's a load we need to meet right now with fossil fuels. But if we could capture some of that heat that is being collected in the cooling during the day and store it, we could use it on the heating side. The challenge is with steam, you can't do storage, and the temperatures don't allow for this type of heat recovery. We can't use the low grade heat that we'd recover from the chilled water system to help our steam system at all when it's such a high temperature system. So without getting into why people designed steam systems in the 60s and 70s when they went in, the real opportunity for us is to get to hot water. And I'm going to talk a little bit about why and some of the opportunities that creates. So we've started a project. Our wonderful campus communications folks came up with a name. It's called The Big Shift, and it's about moving our campus toward a carbon neutral future. And there's a lot of shifts involved here, but the main idea is that we're shifting from a steam-based system to a hot water system. And the full electrification pathway, I guess, we're creating a pathway for full electrification, and that's through heat recovery. But to get to the full electrification, we're going to have to add also some heat sources in the winter. And the best opportunity to do that, the lowest energy cost, would be through geo-exchange or air source heat pumps. So that's still our ultimate goal. I'm going to talk about what we're implementing now and what we're doing next with heat recovery. And then the ultimate goal is to then add in some additional electrification through geo-exchange or air source heat pumps. The challenge is that that heat recovery can happen for 60% of our heating load. We can meet it with heat recovered from our cooling system, but it's the other 40% in the winter where we just don't have enough cooling to recover heat for our heating side. Going back to this chart. So in those winter months when the heating load is highest, at the beginning and end of this chart, we don't have enough cooling to fully meet our heating loads. And so that's the dark red shown there. And that's where we need a supplemental heat source. But if we're using heat recovery, we're able to use real low grade heat. And that's where we can tap into the ground with geo-exchange and just heat our chilled water up. Instead of heating it in the buildings when we're doing cooling, we can heat our chilled water system up in the ground and use that low grade heat then through heat recovery to do our heating. So just as a comparison, steam district heating, and this is really how we've pitched this whole project to the campus administration and got buy-in for it. It's an aging infrastructure that needed to be replaced. If you've been around campus at all, in the winter, you often are going to see these clouds of steam coming out of the ground at various leaks, or whether it's steam or condensate leaks. They'll create these clouds coming out of the ground. That's dollars coming out of the ground. That's money we've spent on gas and on water treatment and on moving that heating source around the campus, and it's leaking out because it's an old infrastructure and because steam and condensate are both very good at making leaks. So we're at a point where we need to invest a lot in this infrastructure. It's been going into the ground for the last 60, 70 years. And much of it is ready to get replaced. We're at a point where we need additional boiler capacity. And the system itself inherently at 350 degrees, it's going to have a lot of heat losses in the distribution. That's something they weren't really considering when they designed these systems. Energy wasn't at such a premium, and that's something you can't really insulate very well at 350 degrees. And so even with good insulation, you're going to have a lot of losses. But with the aging infrastructure we've estimated our distribution heat losses are 30 to 50%, depending on the time of year. And that's because you have to keep these steam lines charged with steam, pressurized with steam all the time, regardless of how much steam you're using on campus. So, in the summer or a day like this, where we're using very little steam, just a little bit of process and some reheat in buildings where there's cooling going on, all the steam system is pressurized and ready to be used. You have to maintain it that way just inherently, and that's going to have a lot of losses. Hot water, on the other hand, if we spend money on this instead of on steam, we're gonna, in addition to a new and more efficient system, will get us a renewal of our heating system. And then there's all the avoided capital costs that we can spend on hot water instead of on steam. There's much lower operational costs. It's been shown in places that have converted, for example, Copenhagen, over 50 years, they've been converting from steam to hot water. They've shown that steam costs 10 times as much to maintain, in addition to the efficiency gains that I'll talk about. And then the big one for us is that it is an electrification pathway. So how did we get there? We did a long multiple year study with consultants and looked at many different options. Ultimately, this is how the campus planning works. We do, life cycle costing and try to pick the best solution. The big challenge for us is still coming up with the capital to do it, but we at least want to know what the right decision is, and then we try to find the funding to do that. So we came up with a couple recommended solutions, both of them involving what's on here called central CHC, which is combined heating and cooling at a central location. That's the heat recovery I've been talking about. And then we're going to try to do the full electrification as well. So what we're not going to do is we've looked at distributed combined heating and cooling, which would be heat pumps at multiple locations across campus, even at every building or in small districts. And that just became too much of a challenge for infrastructure costs on electricity, maintenance costs of all the equipment. So without getting into that, we've landed on what we're going to do, which is centralized heat recovery, and then the full electrification pathway would involve ideally a geo-exchange field to meet the winter loads. What we're doing right now in the Big Shift project is what's called the Hutchison Quad Hot Water Conversion Project, and that's the red shown here, both the red pipelines, which have been going in the ground over the past year. If you've been on campus at all, you've seen that now in California and around the quad, North Quad, and that they're going to be continuing to work on that through the end of this year. And they're just starting on the buildings. The red buildings are getting conversions where they're replacing heat exchangers, the steam to hot water with hot water to hot water heat exchangers, or running hot water directly into the hydronic systems in the buildings. So that's going to be happening as well through early 2022. And then we're going to be moving on to the other districts and the other colors on this campus map. The next project after this is going to include the heat recovery. And that's where the real opportunity is. And this is pretty much where I'm going to end this one is, why do we go to hot water? People might think hot water is not that different than steam. Well, the temperature is different, and that makes a big difference because you can generate these low temperature hot water, which ours is going to be in the 150 to 160 range, from a lot of different sources if you use heat pumps or heat recovery chillers. And obviously, if you can go to even lower temperatures, you can use multiple kinds of heat pumps. But what's really exciting is that when you have hot water, you're able to do storage, and then you can use a lot of the different sources shown here, and you can make your heating and cooling systems work together. And the efficiency gain is really significant. Right now, our systems are completely independent, and our cooling system, as work with a refrigeration system in the chillers, has a coefficient of performance of 3 to 4, which means that for every unit of energy you're putting into it, into our electric chillers, you're able to move 3 or 4 units of thermal energy, which is a great efficient process. But with this new system with hot water, we're able to actually use the energy on the cold side as well as the hot side. So right now we're just making the chilled water and rejecting the heat. But if we can use that hot side as well, then suddenly our coefficient of performance goes from 3 or 4 to up to around 7, because now we're able to take advantage of that hot side heat rejection. So that's where the real benefit comes in, and then able to tap into many different potential low-grade heat sources. Probably for us, the most likely is going to be just a geo exchange, where we can run that cold water into the ground and get it up to a temperature where we can do heat recovery. So I'm not going to spend time on these next two slides. This is showing our existing system schematic and then what the ultimate future system schematic would be. But I'm going to wrap it up there and leave the rest for questions.
Perfect. Thanks, Josh. There was a question here in the chat from Kevin. He was asking if there's any opportunity for renewable natural gas or hydrogen for heating.
Yeah, renewable natural gas is definitely something we talk about a lot at the UC system, and UC Office of the President is actually the owner of several biogas plants now, and with the goal of being able to use that biogas to offset gas usage on the UC campuses. The challenge is there's just not enough of it. And I don't think there's going to be enough of it. That's a market that's growing, but probably not going to be able to completely offset the natural gas, industry at any point in the near future. So some of the other campuses, have cogen systems that they're really tied to natural gas usage. Don't have a lot of options to get out of those. Some of those are even fairly new. And so likely the biogas is going to be mostly used for those type of systems, whereas we have an opportunity to actually get off of gas over the next 5 to 10 years and electrify in a way that's actually going to save us energy and get us to carbon neutrality. So biogas for us hasn't been a real need, but we are still buying into that system right now for the UC system. We're going to be buying into biogas starting in 2025. And so we'll be getting some of those credits as long as we're using gas. As far as hydrogen, that's something that I think is still a work in process. There's researchers, obviously, you probably know, doing work on that. Guy at Irvine has done a lot with that. But it's not something that's going to meet our needs at the scale we're at, as far as I know. So other questions?
Yeah, it looks like a couple got posted in the chat. Jason is asking, during this transition period, are you heating your hot water loop with steam?
Good question. Yes, so this first big shift project that I talked about with the Hutchinson Quad, we don't have the heat recovery chillers yet, and we don't have enough of a hot water system to really put them in yet. So we are heating the hot water with steam in heat exchangers. Thankfully, we were able to get some heat exchangers at almost for free from Stanford University, because they just did this conversion and had some temporary heat exchangers that they didn't need when they were done. So we were able to get their heat exchangers and refit them, and we're using those at our central plant and then also a remote location to do the heating of the hot water for this first district until we can get the heat recovery chillers in. And I see the next question.
Yep, you see the next one? Okay, great.
Phasing plan primarily to address complexity and scale. The phasing is mostly funding. We don't have funding to, like, for example, this first district we're doing is around $50 to $60 million. And that we were able to come up with that through a mixture of, offsetting other capital projects and avoided costs with the steam system. But beyond that, we don't have any available capital to spend on it right now. So we're working on how to fund the rest of the project. But we don't want to wait around, and we need to get it going. And we're figuring that we're able to learn from this first one what actual costs are, and then take some of those lessons learned and costs and apply it to the rest of the project. So we're actively working on getting the design going for the next district with the goal of being able to get it funded and start implementation in 2022 next year, so that we can keep the project moving. And then the final configuration will continue to use our natural gas boilers as long as they have life left, but we don't plan to put in new steam boilers. We would, we're going to have a decision point when our current boilers reach end of life about whether to put in hot water boilers if needed, or if we can just get by with heat recovery and other supplemental sources like air source heat pumps or geoexchange. So we haven't had to cross that bridge yet, but we will. We're looking at those options. Great questions.
Great. Well, thanks, Josh. And I'm gonna, if it's okay with you, I'll share your email in case people have any further questions.
Absolutely.
Okay.
That was the next thing up here. Yeah, send that
Oh,
out.
well, there we
and,
go. All right.
Phil, I can answer questions later for sure.
Sounds great. Appreciate it. Thanks so much, Josh. And
Okay.
let's see, Vinod, you should be able to share your screen when you're ready.
All right, thank you. Can you hear me?
Yeah.
Okay, and see the screen? Let's see if this works. Can you see the screen?
Yes, looks good.
All right, awesome. So I'm going to give you some overview of the modeling work that we've done in a project that recently concluded. It's on a hybrid sub-wet bulb evaporative chiller. Go through some brief agenda here. I want to acknowledge CEC for their funding. Integrated Comfort was our implementation technology partner for the SWEC. The WCC team is listed here, and they all contributed in different ways to the results that I'll be sharing today. So the goal was to evaluate the performance of 2 residential retrofit cooling solutions based on compressor-less technologies. And they were based on the sub-wet bulb evaporative chiller. So this, I'll show you the working principle of it in the next slide. But the basic idea is that you're replacing the energy-consuming compressor and the vapor compression system with an evaporative cooling device. But we had to modify the goal to include a nearly compressor-free system. So we included what's called we ended up developing what's called a hybrid SWEC, which has a combination of a small vapor compression system for an additional boost when it's really hot outside, but mostly running on the SWEC when it's when this additional boost is not needed. So the HSWEC in the slides will be referring to that additional SWEC plus compressor. So here is a picture of the device that ICI built for us. On the left side, if you can see my arrow, that's the hybrid SWEC in operation in a house in Davis. If you open up this panel, you'll see the SWEC itself. It's basically made up of 4 polymer heat exchangers, and in sandwiched in between them is the evaporative media. So the outdoor air comes through, the first heat exchanger gets cooled down sensibly before it enters the evaporative media. The water from the house, from the water coil in the house, comes through the tube here, and it gets sprayed onto the evaporative media here, and it cools. It goes down, and while it goes down the evaporative media, it gets cooled by the air that's coming in, because there's evaporation of water going on, and the cold water is stored in the reservoir down here. You could have a single pass, you can have 2 passes, and the cooled water is used in the house or in the process if it's just a SWEC operation. What we did is we integrated a vapor compression unit into the central column here. So if you pull out this evaporative media and you open a panel, you'll see how the vapor compression unit is integrated there. So there's the compressor here, and this is like a 1-ton system. So there's a compressor here, there's the evaporator. In the evaporator, you have refrigerant here, in this case 410A, exchanging heat with the chilled water that's coming in from the reservoir. So the first stage cools it down, cools the water down, and then it gets cooled down further using this vapor compression system. And the exit of the evaporator, the chilled water goes into the house, into the water coil. And then there's the condenser that sits on top here, sees the cooler, higher humidity air that's coming out of the SWEC. The exhaust air from the SWEC is used in the condenser, so you get some pre-cooling of the condenser. So its performance is actually better than you would have if you had just a vapor compression system sitting outside. So all that, and you see the top fan that sucks in the air through the heat exchangers, evaporative media, and the condenser coils, and sends it out. So that's basically how it looks. In terms of the 2 different schemes of cooling delivery, if you imagine a house with a typical vapor compression system and a standard refrigerant coil sitting in the attic, in one house we tried using this hybrid SWEC system let's start on the bottom with basically replacing the hybrid SWEC system, but using everything else the same, using a water coil instead of a refrigerant coil, but everything else being the same, central system with cooled air being supplied to the rooms by the ducts. In the second system, we said, okay, it's a duct-free delivery system where you have the hybrid SWEC and it's plumbed into smaller water coils that's sitting in different rooms. So basically, your zoning, you can make use of zoning, and then you're reducing the duct, eliminating the duct losses by using this water loop. The central system has a fan coil that looks typically like this. It's a water coil with multiple passes, and then you have air from the house going through it and getting cooled down and to the delivery. For the distributed system, you had these smaller fan coils that sat in each room. I'm going to focus on this one because of time constraints, but we have modeled both of them. Just to show you what the field results look like. So I have to emphasize that when we installed these systems, they were not optimized yet. So we soon learned that the baseline capacity, this was the capacity of the vapor compression unit that was in the house already, versus what we could achieve with the SWEC alone, which is basically the vapor compression system turned off. So just the evaporative cooling part was significantly, it was about a third or lower. And even with the second stage on, we were not able to get the capacity up as much as it was in the baseline. In terms of COP, not that different compared to the baseline system. So this was kind of a disappointment for us. And when we looked at the data, the problem was that the entering water temperature to the SWEC from the air handler was close to or below the wet bulb temperature of outdoor air for most of the hours. So basically, it's not an optimal scenario for the chiller. We looked at different options and we said, okay, how do we optimize the SWEC, the hybrid SWEC, and air handler? And that's where we undertook this modeling effort to see what changes are needed. So briefly, the model looks like this. This part here on the left side is a SWEC model that we had from our prior work. That's, if you're interested, you can take a look at this paper. What we did is that we coupled a vapor compression model. We added a vapor compression model to the SWEC model. So basically, you have water coming in to the SWEC. It's cooled down in the evaporative media. The cold water that's sitting in the reservoir is pumped into the evaporator and sent to the air handler in the house. And so we modeled the plate type evaporator and the microchannel condenser, and the air that's cooling the refrigerant in the condenser comes from the SWEC. We calibrated this model using laboratory experiments that were done in summer. We mimicked the load of the house by a water cart, and we could control the return water temperature into the SWEC, and we chose a couple of temperature points. We varied the flow rate of the pump and the fan speed, and we achieved, and we looked at, I believe, 3 different outdoor air conditions, including temperature and dry and wet bulb temperatures. And what is shown here on the left, on the right side is the results after a calibration. So what we did is there were a few things that we needed to adjust in the vapor compression loop in order to capture the trends. And those are mainly, those are listed here. It's getting into the details, but if you're interested, we can talk about it later. After the calibration is done, you can see the supply temperature predicted by the model and the supply temperature in the experiment, and the parity is pretty good. Same thing for the cooling capacity in tons. This is the model prediction versus the experimental data. So once we were done with this calibration, we coupled this model to a central coil. And so you had chill water coming in from the hybrid SWEC, going into the coil, and then coming out and going back into the SWEC. So this entire thing was coupled, and we call this a system. So SWEC or hybrid SWEC plus air handler, or sorry, water coil is a system model. And we use this system model with the baseline SWEC and air handler that was used in the one of the houses. It was a 6-pass, roughly 2x2 foot water coil, and we saw how the performance predicted compared against the actual data. So here in green is the model result, and in red is the actual measurements from the house for capacity, and for just the stage 1, no vapor compression. And here is the same thing in terms of capacity model versus data for stage 2, that is with the vapor compression on. And you can see that there are transients, but if you don't consider transients at the steady conditions, the match is pretty good. And we didn't expect to capture the transients anyway, because this was a steady state model. So with that, just going back here, you can still see that the performance is pretty poor. We were able to predict the performance, but the performance is still bad. So one of the things that came to our, when we looked at the initial data, it became obvious that the fan coil or the water coil is not really performing well. So we started developing in a different project an advanced water coil made of polymer. And here's an example of a typical finned tube heat exchanger. You have water, air going from left to right and water going in cross flow. What we realized is that the effectiveness of this kind of a coil, which is in cross flow heat exchange, can never be as good as a pure counter flow heat exchange, where the air is going, let's say, from left to right, and the water is going from right to left. And so we developed a microchannel polymer heat exchanger. And we realized again that the resistance is on the air side. You don't need expensive metals. You can use plastic and make a heat exchanger for this application. So we did some lab experiments to validate this design. And what you can see here is the effectiveness, how good of a transfer of heat can you get from the air, from the cold water to air, versus the NTU, which is basically a measure of the performance and the size of the heat exchanger. And you can see that these lines, these points here are the data measured from the experiment of the small scale heat exchanger. And these solid lines here are theoretical counterflow heat exchange performance curves. And you can see that the experimental data sit pretty nicely on top of the theoretical counterflow heat exchangers performance, saying that, and this tells us that you can get a much higher performance than you could with a cross-flow heat exchanger that's typically used in water coils. Here is an example of what the effectiveness would look like as a function of the length of the heat exchanger. So if you think about a water coil that's about 20 centimeters in depth in the direction of the airflow, if you use a polymer heat exchanger, you can get effectiveness higher than 80%, whereas with the traditional water coil, you get around 50%. What that translates to is, if you were able to transfer about 8 kilowatts of heat, with the new polymer heat exchangers, you can get closer to 13 kilowatts of heat instead. So what we did is we coupled this polymer heat exchanger to the hybrid SWEC model, and we did an optimization. So in the hybrid SWEC, just the SWEC part of it, if we increase the depth of the evaporative media from 15 centimeters to 30 centimeters and increase the condenser coil, adjust the fan speed and pump speed, and then you couple the hybrid SWEC to the MPHX, you get an optimal system. And so to show you how the performance of this optimal system compares to what you had in the baseline, we have 5 different scenarios listed here. It's busy. What I want to show is this is the same field data that you saw before in terms of capacity versus time on a couple of days. The black dots here are field data. These darker blue lines are the model that predicts the baseline hybrid SWEC model. I just want you to focus your attention on this set of data and look at the orange line here, orange dots. The orange dots are basically the original dimensions and of the hybrid SWEC. The only thing that's changed is that instead of a water coil, you use the microchannel polymer heat exchanger. And so you can see that the performance jumps from about, let's say, 3,000 watts to about higher than 4,000 with by use of the polymer heat exchanger. Now, if you focus your attention on this blue versus orange, the orange one is basically the original hybrid SWEC with just the microchannel polymer heat exchanger. And now we are just changing and optimizing the SWEC in terms of the condenser dimensions and evaporative media. And you see that this boost you get in capacity is because of the hybrid SWEC optimization. So if you couple that, and then if you do some process variations like varying the water flow rate, you get to even higher levels. So you can see that with a 3 gallon per minute flow rate, with optimized dimensions for the hybrid SWEC, as well as the microchannel polymer heat exchanger, you can get closer to in excess of 5,000 watts, where the original hybrid SWEC was under 3,000 watts. So significant increase in capacity. On the right side, you see same things with performance in terms of COP. Obviously, if you did not use the second stage, which is the vapor compression stage, you have the highest COPs available. But if you did have to use the second stage to increase the capacity, then you're still getting COPs higher than what you had before. Having optimized this system, we said, okay, let's look at how the system would perform in different climate zones in California. And we looked at 2 different sized homes, a small home, which is about 870 square feet, and another one of 2,400 square feet. Climate zone 1 was omitted because there was not much cooling there. Here is an example of an entire year of cooling modeled using this hybrid SWEC model for climate zone 12. This is the COP versus the hour of the year. You can see this is the baseline. A baseline of CO14 was modeled as well. So this orange is the baseline. If you did not need the hybrid SWECs, if you can just manage the cooling load with just a SWEC, you can see a significant boost in efficiency or COP 2 to 4 times that of the baseline system. If you did need to use stage 2 in a few hours, you still see a slight increase in efficiency compared to the baseline because your condenser is seeing cooler air. And so you're getting that extra benefit there. If you replot this data as COP as a function of outdoor wet bulb temperature, you see that you can use the stage 1, which is just a SWEC, evaporative cooling, for quite a bit, all the way up to about 65 to 68 degrees. And then the stage 2 kicks in. Obviously, you have a stronger dependency of COP on outdoor wet bulb temperature for the evaporative cooling device, and even for stage 2, because you you use that moist, humid, cooler air for the condenser. Do this for all climate zones, and on the left side, we are showing cooling energy savings and cost for the smaller home, cost savings, and likewise for the larger home. What you can see is that we have about an annual cooling savings of about 57% for the smaller home if you use this hybrid SWEC. And it satisfies most of the loads except for this climate zone 15, which is an oddball, really high cooling loads. But other than that, we are able to use that the SWEC to meet all the loads of this 900 square foot house. On the for the larger house, you see that again you're seeing savings around 52%. The cooling savings are a little lower here because there are more number of hours where the vapor compression system has to kick in. But nevertheless, you're seeing significant savings in most climate zones. For climate zones 11, 13, and 15, this system had more unmet hours than over 400 hours. So that basically tells us that we need to kind of size this SWEC a little higher, larger for these climate zones. But overall, what we saw was that this system, this optimized system, would work pretty well for most climate zones in California and yield pretty high energy and cost savings. We have to do future research in terms of control strategies, and the MPHX, the polymer heat exchanger, is being developed in a follow-on project. So hopefully it'll get closer to commercialization as that project ends. So the issue with the SWEC has always been that, okay, it provides cooling, but what happens during the winter time when you need heating? So there's a potential to couple the SWEC with a hot water heat pump and use that for providing both space heating and cooling, and also water heating. So that's another thing that could be explored in the future. So with that, I'm open to your questions.
Great, thanks, Vinod. All right, well, if you have questions on what okay, one of them got answered, great. If you have questions, feel free to put them in the chat or raise your hand and we'll unmute you. You can unmute yourself. Nope, we got one raised hand. Let's see.
Was that?
Kelly,
Teresa, go for it.
In the various system models that you tried, I'm wondering if you tried a like a two coils in series, essentially, where the SWEC water feeds the first coil and then the water heat pump feeds the second coil, such that you're not trying to cool the water with the SWEC that returns from the heat pump water, if that makes sense.
No, we didn't try that. I think I guess we did discuss this, if I remember. Maybe Curtis remembers it better. But we didn't want to put two coils in the house, is probably the reason.
Yeah, I mean, practically, I don't know that it makes sense, but it seems like that might actually give you the best. I'm not certain, but I wonder if that would give you the best efficiency result. I was just curious, but yeah, it doesn't seem terribly practical. I have to agree with that.
Right. I mean, putting it in series, you have the fan losses as well. You need to think about if you're not using, especially the second stage.
Yeah. Yeah, I don't know how it would land.
Yeah.
Vinod, I don't know if in the chat, there's another question. It's from Jeff,
okay.
asking where you're doing the testing or whether it's been just modeling so far.
We did. So the non-optimized device that's shown here was tested in 2 houses in Davis. And we did test this in the lab to understand what the optimal flow rates, fan flow rates and water flow rates would be. So we have data from both field and lab, and we use that to calibrate the model. So we haven't tested, we haven't built and tested the fully optimized version yet.